This is your simulation. This is your playground. There are two charges, plus charge and minus charge. They are at the unit of nanocoulomb and 1 point charge is 1 nanocoulomb. There are sensors which you can put as many sensors as you want. Wherever you put the sensor, it will show up the electric field vector at that point and also the angle of the vector, the angle between the x-axis and the vector. This button over here, it will clear everything up. Before I put in charge, if you check the grid box, it shows the grids on the playground. And the grid is, if you put the values in one large square of the grid is 50 centimeters and two of them is 1 meter, as you see over here. I will just put this plus charge, let's over here, and it shows electric field vectors. And if I unchecked it doesn't show now. Well, the direction of the arrow lines clearly represents the direction of the electric field, first of all. But the length of the arrow line does not represent the strength of the electric field, because the length everywhere the same for these arrow lines. The strength is shown up as the brightness of these arrow lines. The brightness is diminishing as you move away from the source. If I put a sensor over here, it shows the electric field vector is a red yellow line. If I put a sensor over here, the electric field vector is a red yellow line, and also it reads the values in over here. It's at the minus 43.9 degrees, and it's at the strength of 3.86 volts per meter. Let me bring this over here. That's somewhere which is at a distance of 2 squares. 2 squares is 1 meter, so it's 1 meter away from the source. 1 meter away from the source, the sensor reads 8.94 volts per meter. But is it true? You can check this in fact. And just so you know, the strength of the electric field is K times absolute value of Q divided by R squared. And R is the distance of the point to the source charge Q. And K is the Coulomb constant and is around 9 times 10 to 9 Newton meter squared over Coulomb squared. So you can check that formula because you have 1 nanocoulomb charge as the origin, and from this point on a point which is 1 meter away, reads the strength of the electric field of 8.94 volts per meter. And you just do this calculation, KQ divided by R squared. Instead of R, you put R is equal to 1 meter, and K is 9 times 10 to 9. And the charge value is just 1 nanocoulomb. 1 nanocoulomb is 1 times 10 to minus 9 coulomb. So you add this whole number and check this whether this number is true. You can check this by running the simulation. And what about else? The thing is that over here you see is voltmeter. It shows a crossbar over here, and right at the center of this crossbar, it shows the value of the voltage at that point with respect to this source. Well, let me bring this over here. That's somewhere which is at a distance of 4 squares from the source. Since 2 of squares is 1 meter, it's 2 meters away from the source. 2 meters away from the source, the voltmeter reads 4.500 volts. But is it true? You can also check this in fact. As you know, the potential formula is K times Q divided by R. So that means you can check that formula, KQ divided by R. Again, you take this point, the location of the charge as the origin, and from this point, on a point which is 2 meters away from the charge, so 2 away, a voltmeter reads potential of 4.500 volts. And just do this calculation, KQ divided by R. You put R is equal to 2 meters and K is 9 times 10 to 9 newtons meter squared divided by coulomb squared. Charge value is just 1 nanocoulomb. So you can check this whether this number is true. So what the other things that this device can do? There are also 2 buttons at the bottom over here. One is in shape of a pencil and the other is the eraser. If you press this pencil button, it just draws a circle around the charge. And that circle nothing but it's the equipotential line. As you know, on the equipotential line, every point is at the same potential. For example, the potential is reading 4,500 volts. If I move this on a green line, I will always read the same potential value. Equipotential line also shows the value over here, 4.5 volts, because I checked the values over here. So if you go over somewhere else and press the pencil button again, you will see another equipotential line will appear. This time, this equipotential line is at 8.1 volts. It's higher potential than this one because it's closer to the source charge. So that goes like this, and if you press eraser, it will erase all the equipotential lines. Let me draw an equipotential line that passes from this point right over here. It's 11.72 volts. Well, the other thing is that you can just check this value from formula. How do you check this value from the formula? You just use the last tool over here. This is the measure tape. It measures the distance between these two orange crossbars. So if you bring the first orange crossbars over the source, and if you extend this second crossbar, write the equipotential line over here, it raised the distance it is now is 76.4 centimeters. So just putting this instead of R in the potential formula, which is KQ divided by R, and Q is 1 nanocoulomb, you will find that a value which is very close to 11.7 volts. You can check this. These all things you can do. Well, what next? Let me show the report. Now you see the report. So what you see, read on the first page is that the title, the link to your simulation and objectives. The objectives is what you will do in this lab for this simulation. You will verify the electric field formula, the electric field for a point charge. You will explore the electric field lines for various charge configurations, and you will verify the superposition principle. The principle of superposition says that every charge in space creates an electric field at points independent of the presence of other charges in that medium. The resultant electric field is a vector sum of the electric field due to individual charges. So you will also verify this principle. And the last, you will explore the relationship between the electric field and electric potential. There are some parts. The report goes part by part. Let me just go over it. This is the first part is about the electric fields and this is the second part is also about the electric field. And third part is about electric potential. And the fourth part is about reaching the relationship between the field and the potential. So there are four parts and last conclusion there. Let's go step by step over all these parts. Let's start for the first part. Electric field of a point charge. This is the procedure. The procedure is number 1, 2. Also conclusion for the first part. And question for the first part. There is a table also in the first part. You will fill out this table by doing some operations on simulation. First item is clicking on the grid, placing one positive charge in the center of the grid and clicking on electric field. That's we've done. After that, you will answer this question. Can the arrows that the program uses to visualize the electric field be called the electric field lines? How they are similar and how they are different from the lines? To explain what we mean by this, let's go back to the simulation again. As the report says, let's click on a grid, place one positive charge in the center of the grid and check the electric field box. The question is, what these arrow lines represent? And the other thing is that the question in your reports asks you that, does these arrows represent the electric field lines? Well, it doesn't represent the electric field lines. If you connect them, it would represent the electric field lines, but this way, they don't neither represent electric field vectors nor represent the electric field lines. Because, first of all, their strength is not represented by the length of the lines, and they are not connected. If they are connected all the way, then you will say that this would represent the electric field lines. But you know you cannot say that, this configuration. So this is the answer of the first item on the first question in your report. What was it? Can the arrows the program uses to visualize the electric field be called field lines? The answer is no, and you should type the reason. Next item in the first part of your report, Clicking on the values and placing electric field sensor, the yellow circles, on 5 various points on the grid. For convenience, choose points on the intersections of the measure grid lines. Measure their x and y coordinates, assuming the point charge is placed in the origin of the coordinate system, and record the following information in the table below. Note the scale of the grid and make sure that you see the correct units. So that means the second item in the first part is to fill this table. So you see in the first column there are 5 numbers over here showing the 5 different sensors. Let's first do this. Let's first come over the simulation. Let me uncheck this electric field. The grid is okay. It says that place this charge at this point and just accept this point, the location of the charge, to be origin. I will put now 5 different sensors. Let me put the first one over here and the second one let's put over here and the third one over here and the fourth one over here and fifth one over here. So I just placed 5 different sensors as the report says. Let me open the report. The first column is just showing the sensors in number. The first sensor, the second sensor, the fifth sensor. So the numbers represents the sensors. You can just label them 1, 2, 3, up to 5. And the second column is labeled as X. That means the X coordinate of the first sensor should be put over here. And X coordinate of the second sensor should be put over here and so on. Also, Y coordinates over here. So the fourth column is something about this calculating. This value x squared plus y squared in this square root, which is nothing but the distance of the location of sensor to the source charge. Let's do this for our case. Let's go over simulation. Check the values. Let's label this one as the first sensor. So what's the X value for the first sensor? Remember that this is the location of the charge is the origin, and to the right, as I just count 2 large square as the distance of X distance of the first sensor. It's 2 boxes, but 2 boxes is 1 meter. So That means x of first sensor is just 1 meter. So what should I do is that I should put one over here. X is in units also. Let me show the unit of X. You should also do this. Unit of X is meters. So I just put one because the first sensor's X distance is located 1 meter away from the source. This is my first sensor and its X coordinate is just 1 meter away from the source. That's why I put one in the box. And what about Y? Let's make me put meters for the distance. So what's the Y coordinate of the first sensor? I just switch to the sensor over here. Its Y coordinate is just again 1 meter away from the source. So I should also put one to the right corner. And next is this R is going to be just calculated as 1 squared plus 1 squared and square root. It's square root 2. This is R over here. You will just type the square root to what square 2 is. You will type not as square 2, but whatever it is in the decimal system. Square root 2 is 1.41 meters. So next is there, you see the angle column. Angle column is just arctangent of y divided by x. Y1 and x1 and arctangent 1 is nothing but 45 degrees. You will just type this angle to be in degrees, so it's going to be 45 for our first sensor. And the next column is this, show the strength of the electric field. The strength of the electric field, you just come over the simulation and you can read whatever it is. Written on the second number on the first sensor, it shows 4.35 volts per meter. So this is nothing but the strength of the electric field at this point. And it's a unit should be type over here. It's volts per meter. or Newton per Coulomb. And next is electric field angle. What electric field angle is to be measured from the sensor? This value over here is, it's 44.2 degrees. Why it's not 45? When I put this sensor right over here, I told it's x is equal to 1 and y is equal to 1. But you know it's not exactly right at this, that the x is equal to 1 and y is equal to 1. It's a little different. So this is an experimental error. You just type, I just read from the sensor is 44.2 degrees. This angle and this angle are not the same, but they are close to each other. Why are not the same? Because I'm doing some experimental errors. I'm doing some experimental errors, or either when I'm reading these values or when I'm putting the electric fields, I thought that the x is equal to 1 and y is equal to 1, but probably it's not exactly the points. These might be the reason. In theory, they must be equal to each other, but since you are doing experiment, they don't need to be exactly equal to each other, and there is no way to be exactly equal to each other because you are doing experiment. So you will do the rest of the sensors, 5 sensors, just what I did for the first one. You will just fill out these columns and rows one by one for each sensor up to 5. And over here there is a note, and over here there is a note that the information on columns 2 to 5 and 6 to 7, these last 2 columns are calculated by the simulator, and these 2 to 5 columns are measured and calculated by you, okay? You have to put your screenshot of the playground of your simulation that you will do. There's a conclusion over here, and in the conclusion of this part, the conclusion says that prove that the electric field of the point charge is radial by comparing your values in column 5, the position angle, and column 7, the electric field. So you'll answer this question. You will answer this and write your answer in this blank region. Just type it. So I will continue with the next question. Calculate the value of the strength of the electric field multiplied by R squared for all 5 sensors. For all 5 sensors, calculate this multiplication. For those, you will see that this multiplication is going to be same for all sensors. Why? The report says calculate this multiplication, calculate this product, the strength of the electric field multiplied by R squared for each sensor. Of course, R for each sensor going to be different because you have sensors located at different points. These are whatever the number of the sensor is, just these are going to be R1, R2, or whatever. If you are talking about the first sensor, R is going to be R1 and E is going to be E1. If you are talking about the second sensor, these are going to 2, etc. So use the strength of the electric field at the location of each sensor and the location distance squared from the origin, from the source charge, multiply by them. Find the value for each sensor. Let's look at this value clearly. This is the strength of E. This E, K times source charge Q divided by R squared. If you multiply this R squared, also you will see that this product is nothing but K times Q. But K times Q is the same for all sensors because source charge Q, which is 1 nanocoulomb for each sensor, is the same. You will check this. You will verify the report. Ask you that you verify this product for each sensor and comment on what you find. Comment on these values. Of course, there are some experimental differences, experimental errors that you do by measuring the location of each sensor, and you will see that this product for each sensor may be a little bit different from each other. But you will see they are very close to each other for all sensors. You have to verify this. There is one more question for the first part. Question is, suppose that you use the negative charge instead of a positive charge and look at the data you recorded in the table, which of the columns will change and how. And use the simulator to check your answer. So what you do in your simulation is just changing the plus charge to -1 charge and keep all the sensors in the same place and fill out this table again for the negative charge and look at the differences. So look at the difference from this first original table and what's going to be changed from this original table if you do everything with the negative charge. Then answer this question. So this will finish up the first part in your report. And the second part, I will go over the rest a little quickly because you know every item is going to be clear once you complete the first part. So what's the second part? Second part, first suggest the procedure, and you will just change the setup in your simulation. Use the charges to create an electric dipole with a horizontal axis, which is x-axis, by placing a positive and negative charge equal in magnitude but opposite in sign. You might put the plus 1 nanocoulomb charge and minus 1 nanocoulomb charge 1 meter away from each other. So let's do that. It tells you. Firstly, just clear your setup. For the pole, I will put my plus charge over here and a minus charge just 1 meter away from the plus charge. I just create a dipole. This is a dipole because it consists of equal charges but opposite in their sign. The plus charge is 1 nanocoulomb and the minus charge is 1 nanocoulomb. If you check the electric field, you will see how the electric field changes around this dipole, or you can uncheck it. So what else? What are you going to do with this dipole? Let's check with what report says. Describe the field at the following locations and explain these results using the superposition principle. On the horizontal axis to the right of the dipole and on the horizontal axis between the charges and the horizontal axis to the left of the charges, on the vertical line bisecting the line segment connecting the charges above the dipole, on the vertical line bisecting this line segment connecting the charges below the dipole. On the horizontal axis to the right, it is. Let me switch to simulation. The part 2 says that once you form this dipole, you just measure the electric field to the right of the dipole anywhere on x-axis. We measure this. And measure the electric field to the left of the dipole on the x-axis. And between the charges. You go over the x-axis and describe it. Once you move away from the system dipole and come close to the system dipole, how does this electric field changes? And does its direction changes if you go away from or come close to the negative side of the charge? Does the direction changes? Well, the direction doesn't change. Direction is always pointing to the left over here. Similarly, similarly, over here, direction is again to the left. Direction does not change as you move the sensor along the x-axis. But as you move away from the system, the strength of the field is decreasing very rapidly. In fact, will decrease 1 over r cube. And this is how electric field changes. You will describe it. And also, you will describe the electric field between the positive and negative charges. So, as you see between the positive and negative charges, it seems that direction of the electric field is pointing to the right always. Wherever you close to positive side or closer to negative side, electric field always pointing toward right. So this is the description, and you will type these descriptions. Well, of course, you can also tell something about the strength. For example, strength which is very near to minus charge, and the strength which is very near to plus charge, and the strength at the middle. It seems that strength is minimum at the middle, and it's increasing as you come closer to the either negative charge or positive charge. So, for example, my description is that over here, the strength of the electric field is minimum at right midpoint, and it's increasing as you move towards the sources. It's increasing from that minimum value as you move towards the source. So this is the description. And other thing is that it tells you that describe the electric field vector bisecting the line between two charges. Bisecting means that the line that the pole is located is x-axis, and if you take the midway point between the sources as the origin of your coordinate system, it asks you to describe the electric field as you move away from the y-axis. This is your y-axis because it's bisecting the line that connects the two charges. Bisecting means that just cutting half. So the report asks you how is the electric field changing both in the direction and the magnitude as you move along the y-axis. So as I move along the y-axis, it seems that the direction of the electric field doesn't change. It always showing to the right. On the negative axis, also on the positive axis, it seems that the direction of the electric field pointing always to the right. But again, as you move away from the system, the strength of the electric field is decreasing. Again, over here, as you move away from the origin, the strength of the electric field decreasing. And you will check this decrease in the electric field goes by 1 over r cube. For example, whatever the electric field strength right over here, let's take this as 1 unit. If you increase this distance twice, if you go to twice the distance, the electric field strength will drop by 1 over 8 because it goes by 1 over r cube, and r is 1, r is 2. Since 2 cube is 8, the electric field strength here must be 8 times less than the electric field here. So just check this both above and below, and you will type your description. So this is about toward the item number 2 of your report. The item 2 is about what I've described just before. So it's only a description, so you don't need to do some numerical calculations. Describe that, fill that following positions or locations. Item number 3 of your second part of the report is there a location where the electric field is exactly 0. Try to find the location of these two charges dipole system. You will try to find just on your screen, of course. If you go to infinity, of course, the electric field will be 0 at the infinity because the distance is infinite. But on the screen, near the electric dipole, can you find the location where the electric field is exactly 0? So, you will answer these questions. I'm not going to answer it. Item number 4 reads, remove the negative charge and replace it with equal in magnitude positive charge. So you will just remove the negative charge in the simulation and put the positive charge. You will have two positive charges and you observe the change in the electric fields. And again, describe the field at the following locations. Explain these results using this superposition principle. So again, you will just describe the electric field at these locations. So you will just do the same with the previous item, but this time you will replace the negative charge by a positive charge. I think this is going to be clear for you. So number 5 in part 2, is there a location again where the electric field exactly 0? So once you replace the negative charge by positive charge, you don't have a dipole anymore, because dipole is defined to be you have two charges in equal magnitude, but they are opposite in sign. Only in this case do you have a dipole. Otherwise, it's not a dipole. For this system, which is not a dipole, can you find the location where the electric field is exactly zero? So again, you will check this by simulation and try to answer it. So number 6 of part 2 is remove these charges and then arrange exactly 4 charges, 2 positive and 2 negative on the grid in a way that the electric field is in the center of the grid is 0. Insert the screenshot in taken. This is clear also. This time report says you to do in fact 4 charges, but 2 of them positive, 2 of them negative, and you will put these 4 charges on the grid. In that way, the electric field should be 0 at the center of these charges. You can try the corner of a square. Each corner will have a charge, and check with sensors the middle of the square, geometrical center of the square, whatever you have a 0 electric field or not. So try to catch a 0 electric field at the center. Wherever put these 4 charges, I try to find the point where the electric field is 0. And once you accomplish this, take a screenshot of this arrangement and put that screenshot over here on this. Number 7. Use as many charges as you want to create a configuration of charges that results a uniform electric field in some region of the grid and insert the screenshot of the symbol. If I create 2 large parallel conducting plates charged in opposite charges, I can create a uniform electric field between these plates. But how can I represent these plates in the simulation? Since the simulation is 3D, I can represent the plates with continuous line charges. But how can I create them? One way doing this, putting the charges very close to each other. I'm doing uniformly a positive charge line. It's very time consuming to do. And let's do a uniformly negative charge line parallel to this. So let me turn on the electric field. Well, you'll see electric field lines as you put these charges on the line. Somehow these charges will create a uniform electric field. It seems that somewhere over here, electric field lines always pointing down. You have to make your lines long. Well, let's cut the electric field and put sensors at the interior region. It seems that the directions are almost constant, and also it seems that the strength are also almost constant. So we can see that the field is uniform in the interior region between the lines. And so this will finish up the second part in your report. Next part is part 3, and this part is about electric potential. I will not continue with this simulation because you have learned well how to use it in the first two parts. I think everything is clear what you should do and what's asking you to do. I will just talk about what we expect as a result. For example, for part 3, it's a procedure starts clear all the charges and place one positive charge in the center of the grid, and on the intersection of major grid lines, grab a voltage sensor and move around this voltage sensor around the grid, observing how the values change. And then do the same for one negative charge in the center of the grid, and just compare the readings of these voltage sensor. You will see that the voltage sensor always will measure positive values for the positive charge, negative values for the negative charge, because voltage can be positive or negative. And also you will see that the voltage is inversely proportional to R, which is the distance of the point to the source charge. So, number 2 of part 3, create a dipole again as in the second part. Create an electric dipole by placing one positive and one negative charge on the horizontal grid line. Measure the electric field and the electric potential to the point midway between the charges at the several points on the vertical line bisecting the line segment connecting the charges. Same thing, line means the y-axis. Let me ask you this for a dipole. Is there any point where you measure a zero voltage? And you will think about this. So, number 3 of part 3, create a charge configuration which is similar to that of a dipole but use two charges in the same sign. Measure the electric field and electric potential on the y-axis. Answer the question. Based on your data, what's the main difference between the superposition principle for the electric fields and electric potential? I will not answer this question. You will answer this question based on your observations at the item 2 and 3. I think everything is clear. And there is also part 4. Part 4 about both electric fields and potentials, and about equipotential field lines. Part 4, start placing 4 charges, 2 positive and 2 negative, at 4 random points on a grid. Click on values, drag the voltage sensor in the vicinity of the charges, and click on the pencil icon. A line will appear labeled by a number. Move the sensor in a way such that the intersection of crosshairs remain on the line. Does the number on the sensors change? What's the physical meanings of this line? I've explained this line for a positive point charge when I explained the simulation. As you know, you will see that the value of the sensor doesn't change because this line will be the equipotential line. And then move the sensor to a different spot and click plot again. In this manner, create 8 to 10 lines. And then take an electric field sensor and move it on the equipotential line. What can you say about the way magnitude and direction of the electric field changes as the sensor travels around the line? Since the electric fields due to the individual charges can be added according to the relationship between the directions of the electric field vectors, the net electric field on the line will be not get the same value at every point, but every point on the line will be vertical to the line. Let's go on with the place a few electric field sensors in a few points between the equipotential lines. Where do the electric field vectors point in terms of increase and decrease of the values on the equipotential lines? If you place the electric field sensors between the equipotential lines, you will see that they will always point in the direction of decreasing electric potential. So, there is the last item of part 4. Remove the charges and place the positive charge in the center of the grid. Draw 5 equipotential circles with the potentials of 10 volts, 8 volts, 6 volts, 4 volts, and 2 volts. Take an electric field sensor and move it in a straight line. For example, on the x-axis, crossing the equipotential lines, describe the relationship between the distance between the equipotential lines and the strength of the electric field. Well, this time you will see that the values on the line is getting smaller and the lines are getting farther away from each other as you move away from the charge. And you will see that electric field is always pointing lower potential. And the last, there is a conclusion for part 4. In the conclusion, you should explain all the items which I explained most of them. So this will finish up your report.